Hello, Akshay sir.
Yeah, hi. Can you hear me?
Good morning. So, shall we start the session, sir?
Yeah, we can. Yeah.
A very good morning to one and all present here. On this pleasant morning, I feel privileged to welcome you all on behalf of the EC department for TechUp3 sponsored 2 days online workshop. TechUp3 sponsored 2 days online workshop on IoT and machine learning algorithms towards smart ecosystem during 25th March 2021 to 26th March 2021. Thank you for joining us with this workshop. I extend a warm welcome to our resource person, AkshayNambi, Senior Researcher, Microsoft Research, India. I am also very happy to welcome all the participants, my colleagues and students. Now I call upon Dr. M. Punguri ma'am to give us a brief introduction on the workshop.
Good morning, Madam Professor. Good morning, sir. On behalf of our department and my own behalf, I welcome you all for TechUp3 sponsored 2 days workshop, online workshop on IoT and machine learning algorithm to smart ecosystem during 25th March and 26th March. So it gives me a great pleasure of CIT, and the goal of this workshop is to provide an overview of recent state of art of IoT technologies and machine learning algorithms for smart ecosystems. So in day one, session one of this workshop will be on dependable IoT, improving IoT sensor data quality through robust sensing, and shall be dealt by Mr. AkshayNambi, Senior Researcher from Microsoft Research India. And session two of this workshop will be on Introduction to IoT Technologies, Future Trends, Applications and Challenges, and shall be dealt by Dr. U. Srinivasalu, Assistant Professor and Computer, former Associate Dean, Department of Computer Application, NIT, Trichy. Day 2, Session 3 of this workshop will be addressed by Mr. Amit Chatterjee, Intel Corporation, Bangalore, Industrial IoT Segment Marketing Leader on AI in Manufacturing. And session 4 of this workshop will be on Opportunities and Challenges in IoT Applications and shall be dealt by Professor Tapan A. Gandhi, Associate Professor, Department of Electrical Engineering, Indian Institute of Technology, Delhi. I sincerely hope that you will be benefited by this workshop and have a wonderful days ahead of you. Thank you.
Now I call upon Ms. Dhanlakshmi ma'am of our department to give a brief introduction about our chief guest, AkshayNambi, Senior Researcher at Microsoft Research India.
Good morning all. It is an honor for me to introduce our resource person, Mr. AkshayNambi, who is going to deliver a talk on the topic Dependable IoT, Improving IoT Sensor Data Quality Through Robust Sensing. Here is a brief introduction about AkshayNambi. AkshayNambi is a senior researcher at Microsoft Research India. His research interests are broadly in the areas of artificial intelligence, Internet of Things, and edge computing. He is particularly interested in designing end-to-end systems for societal problems at scale. His Recent projects are focused on improving data quality in low-cost IoT sensors and enhancing performance of DL tasks on resource-constrained edge devices. Now, I call upon Mr. AkshayNambi to deliver his talk. Sir, you can take up the session.
Yeah, thank you. Yeah, thanks for inviting me here. Um, Let me share my screen. Let me know when you're able to see my slides. Is it working?
Sir?
Yeah.
Yes, sir. It is visible, sir. Visible, sir.
Okay, just 1 minute.
Okay, sir. அவரோட ப்ரொஃபைல் ப்ரெசர் பண்ண மாட்டோமா இதுல
So you can see the slides, right?
present பண்ண
Hello.
Sir, your screen is visible, sir.
It's in full screen mode, right?
Yes, sir, it is full screen.
Okay, great. Thank you. Yeah, hello everyone. I'm AkshayNambi. I'm a senior researcher in Microsoft Research India. So I did my PhD a few years back in TU Delft in the Netherlands. So today I will be talking about a project called Dependable IoT, whose aim is to improve IoT sensor data quality through robust sensing. Right? So let me start. So today we all know IoT sensors are being deployed across numerous verticals, right? From transportation, logistics, utilities, smart cities, smart building, consumers, environment, agriculture, right? Where sensors are being deployed to monitor the environment, collect the data, and then take some decisions, right? For example, in smart cities, there have been sensors deployed for parking, waste management. In smart buildings, as we know, there are tremendous amount of sensors for home automation, like PIR sensors for automatic turn on and turn off lights, smoke detectors, and so on. And recently, there's also been significant push in both industrial setups where there are sensors being deployed to improve operations, process monitoring, maintenance, and things like that. And also, there is a significant interest in deploying sensors, IoT sensors, for environment monitoring and agriculture also, right? Where people are deploying sensors to measure air pollution, for example, to measure traffic, to understand how the farm is growing, example, right? Like what is the soil moisture values, what's the soil temperature, so that users or developers, right, can take right actions based on the data. And given the significant amount of sensors being deployed, there's tremendous amount of data, right, which is going to be generated. And this data, right, has significant potential to make an impact, right? And the way impact happens here, right, is by improving the process efficiency, right? For example, only when there is lack of water in an agriculture farm, only then you turn on a motor, right? So you would save power, you would save water, like that. For each of this data coming through, there is significant actions being taken. The agriculture farm is one example. On the extreme end, right, you can think of drones or self-driving vehicles, right, where sensor data is being used to take significant decision whether a vehicle should stop or should proceed and things like that, right? So the data becomes very critical. And as I was mentioning, data quality, right, plays a vital role in increasing adoption of IoT devices. So if you look at the traditional IoT deployments, right, what happens is you have at the lower end, you have these IoT sensors, which is being deployed in various verticals, right? Could be factories, environmental monitoring, smart grids, and things like that, which is collecting the data and sending it to an edge gateway and eventually to cloud, right? Where all this data is aggregated and there is some analysis done, right? So that the user can get insights and can take decisions, right? And in this entire pipeline, over the past decade, right, there has been significant work which is being done. starting from how do you make these sensors low cost? How do you make them scalable, right? These are things which people have been trying to work on that, and they have made it successful. For example, we can buy sensors even for less than 500 rupees today, right? Which could be monitoring temperature, any of those things. And there's also been significant work done in the cloud, right? Where once you get the data, there is a lot of ML algorithms, AI algorithms, right? Which can analyze this data and identify patterns, insights, anomalies, right? Which can help users to make some decisions on the data. However, what we have found, right, is over the past decade, one of the crucial bottleneck in this entire pipeline is the sensor data. So we say sensor data is the weakest link in this entire pipeline, mainly because these sensors, right, are of low cost components, right? And imagine when a sensor breaks down. Think of an example where your temperature sensor, right? I'll take temperature as an easy example. Let's assume that the temperature sensor which you have deployed in your house was broken, right, for whatever reason. Then what happens is the temperature sensor doesn't stop sending data. It still keeps sending some data, but this is garbage data right now. And this garbage data then goes all the way to the cloud, and that pollutes the entire data ecosystem, right? So your insight, or basically your patterns and insights what you derive, is only as good as your data. So if you feed in junk data, your output will also be garbage, right? So it's basically garbage in, garbage out. And today, as there are many organizations and industries trying to deploy IoT sensors, right? They are actively looking at ways, how do you determine whether the data sensed by the IoT device is accurate or not, right? In other words, how do you determine what is the quality of the sensor data coming from the field, right? That is the key question which is being answered, which is being asked by several people here. By the way, please interrupt me at any point of time if you have any questions, or if you are not able to follow anything. I'm happy to answer it immediately. Okay. So the sensor data, right? We are not the first ones to say sensor data is not good. There are several reports, right, which says, for example, here CTO of GE Digital says that about 40% of all IoT data, right, is spurious. And then there is other quotes which says 84% of the CEOs who are deploying IoT sensors, right, they are concerned about the quality of the data. And eventually, right, bad data simply means a butterfly chain effect, which means you pollute the data lake, you take bad decisions, and you will result in bad business decisions, right? So data plays a critical role. So now let's understand, why does the sensor go bad, right? First, if you look at the typical IoT sensors, they are deployed in the wild. In the case of agriculture monitoring, right, these sensors are deployed in remote agriculture fields to measure moisture, temperature, and so on, right? And because they are deployed in the wild, there are scenarios where the sensors can break because, for example, a vehicle ran over it, a tractor, human error, any of these reasons, right? Because of these reasons, sensors can go bad. The other reason is these are deployed in harsh environments. For example, if you are measuring pollution in an industrial setting, right, you are now deploying this in high temperatures, right? So there are chances because of which the sensors can go bad. And also, eventually, right, most of these sensors are made of low-cost components. Right? Today, IoT can achieve 20 billion or 30 billion devices only if the cost is low, right? So because of that, typical IoT devices are always made of low-cost components. Of course, there are certain scenarios, like if you think of aircrafts, right? There, the use of low-cost sensors is very minimal. But apart from few selective domains, in majority of the domains, right, people are using low-cost sensors, and that is the other reason, right, why reliability is a big problem. Now, let's understand what does a sensor fault means, right? So here is a typical IoT device, right? It has a microcontroller, it has a radio, and a battery, right? And to this IoT device, you attach bunch of sensors, right? It's like moisture sensor, temperature sensor, pressure sensors. Now, these sensors can go bad for numerous reasons. It could be sensor defect, it could be sensor damage, it could be sensor drift because of wear and tear, it could be sensor has gone out of calibration, it could be human error, right? Or also even environmental factors like dust covering the sensor or mud covering the sensor, right? Because of all these, and also numerous other reasons, because of which what happens is sensors go bad. And when sensors go bad, the data what sensor generates also goes bad. Okay. So now let's see how are people actually solving this today, right? So I'll take an example of data-centric algorithms. What data-centric algorithms does, right, is it identifies anomalous data in the sensing data. Okay, and then what it says is one approach is if there is any anomalous data, that means it implies there is also a faulty data. So here is an example, right? X-axis is time, y-axis is soil moisture in percentage. As you can see, the soil moisture sensor, right, is giving very constant values, so several days, and then there is this region highlighted in red, which shows for 2 days, the soil moisture values are very high, and then it comes back to normal, right? Now, what data-centric algorithm does is, it identifies that, oh, there is some anomaly here, and then it is saying that this anomaly is faulty data, right? That's what data-centric algorithms can do. It can analyze the previous data and then say, oh, is this data diverging from the previous data? However, not all anomalous data needs to be faulty. For example, you could have high soil moisture value in these 2 days because somebody could have poured water there, or it could have rained in those 2 days, right? Because of which the soil moisture values could have increased, right? So to accurately detect this as faulty or not, right, you would need some historical data or contextual information such as did it rain on those 2 days? Did somebody pour water? And what is actually happening, right? So without this additional information, there is no way you can tell whether this is faulty or working data. Okay, and there are other algorithms, and then there is the scenarios where an anomalous data need not be faulty. Okay, what I mean by that is, here is an example of air pollution data, right? So there is an air pollution sensor here, which is measuring a very high value of 432. Okay, and then if you look at Mumbai and the rest of the city, right, they are measuring an overall value of 95 and 300, right? So overall city is measuring this, but this particular location is measuring very high value, right? So if you use data-centric algorithms, you can simply easily detect, oh, there is an anomaly here, right? But this anomaly does not mean faulty data, because in this case, what actually happened was there were people working on nearby the sensor, and the dust from the nearby working site, right, was increasing the sensor value. So this is not an anomalous, right? Which means this is not faulty data. Now, how would you identify this? Assume this is now deployed in some remote location, right? And all you're getting is just this data. Is there a way for you to tell, is this data valid data or not, right? And today what people do, right, to address these problems is they use sensor redundancy. That is, everywhere I deploy one sensor, I put 2 additional sensors, so that if all 3 of my sensors gives the same value, right, then it means they are measuring the correct data. However, the challenge, right, is the cost of deployments of more sensors is now increasing, right? So this is not, again, acceptable. The final example what I have, right, is not all faulty data needs to be anomalous. What I mean by that, right, is here are 2 soil moisture sensors which is giving some data in the field. Okay, now one of them is faulty here. If you look at just the data, right, it is not easy to say which one of them is faulty, right? Because there is no anomalous pattern as such, right? It's just both are saying one is around 20, other one is around 35, right? It's just giving some data, but it is not anomalous data, right? And which simply says that not all faulty data needs to be anomalous. And in these cases, right, to identify if there is a fault or not, the only way to do that is using human intervention. That is, you have to send a person to the deployed location to figure out whether there is a fault or not, right? And as you can see, it's not easy or trivial to detect faulty data by looking at just sensor data. You have to rely on either contextual information or sensor redundancy or human intervention, right? Which is all expensive, time consuming, and also not feasible, right? Imagine there is a sensor deployed in North India, in Delhi somewhere, right? And let's assume you are in Chennai as an example. Then you have to send a person all the way from here to Delhi to just figure out whether the sensor is working or not, right? Which again becomes infeasible. So the key point, right, is dependability of IoT data, right, is fundamental to realize the IoT potential. Especially if you're taking decisions based on IoT data, right, then you have to be sure that this data is valid data, right? So what does dependable IoT means, right? So dependable IoT means any device which is both reliable and trustworthy says that it is a dependable IoT. And now, what are some key properties of dependable IoT, right? The first key property of a dependable IoT device should be that it should be able to detect and isolate faults in the device automatically, right? Second, it should be able to quantify what is the data veracity, which means what is the accuracy or quality of the data it is sensing, right? Third one, it should be trustworthy, which means assume you have deployed a device in some remote location. How do you know is it the same device which is sending data? Somebody could have counterfeit that, somebody could have replaced that, right? So you want to ensure the device which you have deployed is the same device, right? So that is device signature. If we have all these three properties, then a device is both reliable and trustworthy, which implies it is a dependable IoT device. Okay. So to address the challenges what I mentioned, right, in terms of detecting faults, what we have developed a state-of-the-art solution called sensor fingerprinting. What it means is we have designed intelligent techniques which goes beyond data-centric algorithms to uniquely identify sensor characteristics by monitoring its electrical properties. In other words, what we are saying is that for every sensor, we come up and identify a sensor fingerprint. And then we are saying that each of these fingerprint for a sensor is unique, right? Now, if there is a change in the fingerprint, we know that the sensor is faulty. So think of this as a unique identifier, right? Like Aadhaar ID, right? For each person, we do have an Aadhaar ID, right? Now, let's say for every sensor, we are now providing a unique identifier, right? And then if that identifier changes, then we know that there is a fault, right? Now the question is, how do you come up with such a unique fingerprint, right? That's where we use electrical properties like current and voltage to come up with a unique signature. I'm going to talk more about that in the next slides, right? But the key properties of this fingerprint, right, should be such that it should ensure that we can enable data reliability at the device level. That's the first property which we want. Second, it should work on all commercially off-the-shelf sensors, right? That's the second one. The third one is we don't want to do any hardware modification to get this fingerprint, right? So it should be as seamless as possible. So those are our key requirements here. Now, I'm going to present to you few hardware fingerprints which we have designed. So first one is called fault curve, which is basically a sensor fingerprint to detect faults in analog sensors. So this work is presented in a conference called Census, which is a top conference in sensors and systems. The second fingerprint what we have designed is called current sense, which is a fingerprint to detect faults in electromechanical digital sensors. This work again is presented in a top conference called Iot DI. And finally, we also have a fingerprint which is called IoT ID, which is IoT identifier, which basically assigns each IoT device a unique identifier. Right? So that work is again presented here in Iot DI 2020. All these are published work. So if you are interested in any of these things, right, please visit the website for the project, which has more details there. Now, in this talk, right, what I'll do is I'll focus on these two fingerprints and show you how it works, number one, and how it can be used and how it is deployed. Okay. So let me start with fault curves. Let me just pause here and see. Do you have any questions till now? Okay, I will then proceed. So let me start with fault curve, right? So fault curve, as I mentioned, is used to detect faults in analog sensors. So fault curve, what it does is it basically measures what is the voltage response after you turn down the sensor. Let me explain this more clearly. So here is how you would connect a sensor to a microcontroller. Assume it is an analog sensor, right? You will have three wires, basically the data line, ground, and power. So these are the three lines which you would connect to a microcontroller. Now, let's see how the data flows, right? So across time, the sensor output, when the sensor is off, right, your data is low, right? And when you want to measure something, so for example, let's say we want to measure moisture, right? You would turn on the sensor, collect the data, and you would turn it off, right? So this is how you would typically expect how a sensor should work, right? Now, what actually happens, right, is after you collect the data, when you turn off the sensor, right, it doesn't go down immediately, but it goes down with the following a curve, right? And this curve is what we call as fault curve. Okay. Now, why does this curve occur, right? Imagine if this sensor is a capacitive sensor, then you would see a nice exponential curve here saying it is a, which is a fault curve. If it's a resistive sensor, then it will fall down immediately, right? So basically this curve is saying that after you turn off, there is some charge which is still left in the system, right? Which takes some time to go down to 0. Okay. Now, this fall curve, right, has some very unique properties, right? The first property, right, is this fall curve unique for each sensor, right? So here is some circuits of a soil moisture sensor and the light sensor. As you can see, each sensor has distinct resistive and capacitive components, because of which each sensor has its own unique curve. For example, here is the fall curve for various sensors from accelerometer, current, all LDR, line, soil, sound, right? So for each of these sensors, we have unique fall curve, right? Which indicates that you can now, by just looking at this curve, you can now detect which sensor it belongs to, right? For example, this blue line here indicates that it's an accelerometer sensor, right? The green line indicates it's a line tracker sensor, right? So basically identifying that each sensor has a unique fall curve. Second, are fall curves different for sensors from different manufacturers? So for example, here are two soil moisture sensors from two different manufacturers, right? Both are capacitive sensors, but what changes, right, is just the electrical, the components what we are using, right? The resistor. Sorry, are you still able to see my slides?
Sir, it was visible till now, sir, but now we cannot see it.
Oh, just give me a second. Sorry for that.
Just now. Okay.
Okay, let's see. Can you now see it again?
Not yet, sir.
Now?
Yes, sir, we can see it.
It's in full screen, right?
Yes, sir, it's in full screen.
Okay, great. Yeah. So as I was saying, these are two soil moisture sensors from two different manufacturers. And what changes between these two sensors, right, is just the fact that the components what is used by different manufacturers changes, right? And because this components changes, the capacitance and resistance of the overall sensor also changes, which means for two different manufacturers, you will get two different curves, right? So now, sorry, there is some issue. Yeah. So now, not just that I can detect it's a soil moisture sensor or not, I can also say whether this sensor is from manufacturer 1 or manufacturer 2, right? So that's the key advantage of this fall curve. The third question which can come up, right, is does this fall curve change for a faulty sensor, right? That's our key property which we are looking, right? That is this fingerprint what we are devising that should change if there is a fault in the sensor, correct? So let me explain that, right? So what happens is when a sensor is faulty, right? Imagine a sensor is broken or short circuited. In that cases, the effective R and C values also changes, right? Which would then show up in the fall curve. For example, here is a temperature sensor over time, okay? And you can see both these temperatures are giving some valid value, right? So for example, this sensor is giving around 18 to 20 degrees. The other one is giving around 25 to 30 degrees, right? If you just look at data, it seems like both are working sensor, right? One is in the cooler region, one is in the hotter region. I think that's what we would infer. But let me tell you that one of these sensor is a faulty sensor. Okay, now if I ask you which one it is faulty, it's just impossible to say, right? However, if you now look at the fall curves, this is the fall curve for the blue sensor, which you could see having some fall here. And here is the fall curve of the red sensor. And you can see this fall curve is quite distinct compared to this one, which indicates that this sensor is a faulty sensor, right? Which simply means that by just looking at the fall curve, we can now detect which sensor is working and which sensor is not working. Okay. The final and the most important property, right, is does this fingerprint depend on the environment? Which means, let's assume I collect a fingerprint at high temperature and tomorrow, let's say we deploy that sensor in a low temperature, does the fingerprint change, right? That's the question. Since we are collecting the fingerprint after turning off the sensor, right, it does not depend on the environment itself. Let me explain this with a graph, right? So here is over time, this is the data coming from a sensor, right? At this point, I turn off the sensor. The red sensor was measuring moisture, soil moisture at 65%. The blue sensor was measuring at 55%. So both are measuring different values, but as soon as I turn it off, right, both of them have the same fault curve, right? Which means it does not depend on the environment in which the sensor is being deployed. Okay. To summarize, basically, the key properties of fault curves, right, are it is unique for each sensor, it is manufacturer dependent, it is independent of the environment, and it can easily distinguish between a faulty sensor and a non-faulty sensor. Okay. Now, with these properties, we can now apply this for two very important applications, right? One is fault detection, the other one is sensor identification. I'll explain both of these in the next slides. Let's start with fault detection, right? So I'll take an example of agricultural monitoring. For example, we have this project called FarmBeats, where the idea is you deploy IoT devices which has soil moisture, temperature sensors, and pH sensors, right, in the field all across, right? And then you use drones, right? So this is the IoT device, right, which is collecting the sensor data. And then we have drones which goes over the farm, right, and collects images, okay, which is basically aerial imagery. And then what we do, right, is we combine this soil data plus the drone data to create heat maps, right? Heat maps basically says which region in the farm requires additional water or requires fertilizer, right? So those are heat maps which is then provided to the farmer who can then take some actions, right? Now, in such a setting, you are now deploying hundreds of these sensors across a large farm, right? We have to understand whether the sensor is working, faulty, what's actually happening, right? So let me take an example. So here is a sensor, here's a broken sensor, here's a working sensor. This is a soil moisture sensor. This is how it looks, which is deployed in the field. Okay. Now, this is the sensor data coming from these two sensors. As I told you in the beginning, right, by just looking at this sensor data, it is impossible to tell which one is a broken sensor, right? Now, if I look at the fault curve, that is the fault curve for the red sensor is this, and the fault curve for the yellow one is this, and you can clearly see the red sensor as a distinct fault curve, which indicates that the red sensor is the broken sensor, right? And you can do that only using fault curves today. Otherwise, you have to send a person to the farm, right, to figure out whether the sensor is broken or not, right? And basically, our system has over 96% accuracy based on extensive evaluation in detecting sensor faults, and we can detect the sensor faults with very minimal energy overhead, which means, as I said, we are collecting this fault curve after turning down the sensor, right? Which means we are not consuming any power apart from just reading sensor data, right? So the energy overhead is very minimal. Let me give another example to you, right? So this is the graph which I showed you in the beginning, where I said for 2 days there is high soil moisture values, right? Now we have to understand, is there a fault here or is it working data, correct? So one way to do that is contextual or nearby sensors, right? Which says, oh, did somebody pour water? Or if I know the sensor next to it is also giving same behavior, then I know it's working, right? Now using fault curves, let's see how we can detect this, right? So first what we'll do is, I'll see what is the fault curve before this fault occurred, right? So this is the fault curve of how the sensor is behaving before this red region. And then I'll also see how the fault curve is after the fault occurred, right? So for example, you see both these ones, they are pretty identical. Now let's examine what is the fault curve in this region, right? So if I observe fault curve in this region, you can see there is a different pattern compared to the before and after, right? What has actually happened in this case was that, as I showed you in the previous image, the soil moisture sensor was put inside the mud, and because of the tractor rolling over, right, there was some malfunction in the device, because of which the data was giving garbage data for 2 days. And then when the sensor was clean, because of rainwater, then it became normal. That is why it came back to automatically to normal, right? So what we have done in this project is basically we have extensively tested this fingerprint. We have deployed over 20 IoT devices. Here is a IoT device, right? This is an IoT device, and here are the sensors which is deployed in the farm, right? And the device basically has a microcontroller, battery, and other components. And each device basically has 2 moisture sensors, 2 temperature, and 2 humidity and ambient temperature sensors, right? And what we observed is for 3 months of deployment, right, around 10% of data what we are gathering was kind of faulty data. Okay. And now I will tell you how do you detect faulty data, right? So what we have done, right, is we have created an ML algorithm which can analyze this fault curve fingerprint and automatically detect whether this is working sensor or a faulty sensor, right? So the problem is basically mapped to a classification problem. So to identify this, right, the first step is before we deploy a sensor, right, we first collect the fingerprint for each sensor type, right? So we'll create a database. Let's say I have 3 sensors: moisture, temperature, humidity. These are my 3 sensors. For each sensor, I collect the fault curve and store it in a database. Okay, that is the sensor type and features. And then when the device is running in the field, right, then it will collect its own fault curve, and then we do a nearest neighbor search, right, to the database. So for example, let's say I have a temperature sensor. Its fault curve should match to the temperature sensor in the database, right? If it does not match with any of the sensors, then we detect that as a faulty sensor, right? And we have used nearest neighbor search algorithm called ProtoNN, which is designed in Microsoft Research. And this algorithm, right, is one of the state-of-the-art algorithms which can run on even a simple low-cost, low-resource constrained device such as Arduino, right? And we tested this algorithm on 10 devices, right? And our fault accuracy is over 99% in detecting whether a sensor is faulty or working. Okay. And then now that we are able to detect faults, right, you can now decide how frequently do you want to detect faults, right? Let me give you an example, right? So think of aircraft scenario, right? Let's assume you are monitoring temperature inside the aircraft cabin, right? It's a very important application, and you are taking decisions, right, in controlling the temperature. So every time I sense temperature, you want to know whether that sensor is working or not, right? So you will have high. Every time you're sensing data, you're now also measuring whether it's faulty or not, right? That's one extreme, right? The other extreme is think of agricultural farm, right, where you're measuring soil moisture, which does not change that frequently, but let's say it might change once every 3 hours or 6 hours, right? So in that scenario, you don't have to do fault analysis every data point, but you can do once every 3 hours or 6 hours, right? What the different fault analysis schemes what we have presented, right, simply says you can trigger the fault scheme for every typical sampling interval, right? It could be every 1 minute, every 10 minutes, every 1 hour, or every 1 day, right? That's sampling interval. The second one could be event triggers, which means whenever I see that sensor data is having an anomaly or something, right, only then I figure out whether this is working or faulty sensor, right? And third one is a combination of these two, which says if there is some kind of anomaly, I'm going to check whether it is faulty or not. Otherwise, I will always do every 1 minute checking whether there is a faulty or not. Okay. And here is basically the results. The first row, right, is if I don't use fault curves, right, if I just look at sensor data, I get the F1 score of just 60% of whether a sensor is working or not. However, if you use the fingerprints, you can see across any scheme, right, we are over 95%, right? And the best scheme is hybrid, which says every 6 minutes, if I check whether the data is faulty or not, I can detect all the faulty data with 95% accuracy. Right? That's what this table is saying. We simply use configurations for users to figure out how frequently they want to do this. Okay. Let me go to the second use case, which is sensor identification. So as I told you, in each IoT device, you can connect multiple sensors, right? Now, what happens, right, is for example, let's say I have a temperature sensor, right? what the device will read is just the raw data, which is just analog data, right? And then you have to apply some kind of calibration algorithm or some processing formula, right? Which takes the analog data, converts into temperature, which is degree Celsius, right? That's what the algorithm will do here, right? And for you to apply that algorithm, you have to have this information, right? That is, I have connected temperature sensor in port 1 of the device. I have connected moisture sensor in port 2 of the device, right? So what is actually happening behind the scenes is that based on which port the sensor is connected, for that port, you're applying this formula, right? So if temperature sensor is in port 1, you're applying the degree Celsius formula for port 1. If the moisture sensor is in port 2, you are going to apply moisture processing formula for port 2 to give you the data in percentage, right? So the critical information which you have to remember is for every sensor type, which port is it connected to? These are information, right? Now, imagine a scenario in the field, somebody changed these sensors, right? Then what happens? Your moisture data is going to temperature and your temperature data is going to moisture, right? And which is just impossible to detect just by looking at data. Let me show you an example, right? So I have a sensor and these are the data coming from the sensor, right? As I show you, this is the raw ADC data. Now I know this sensor is a light sensor, okay? So I apply a formula for this light sensor, and now this raw data, you see, it converted to illuminance, right? Which makes sense. Basically what this is saying is there is high illuminance and then the illuminance goes down, right? But what if I tell you that at this point, I changed the light sensor to a temperature sensor? You see, by just looking at this plot, you cannot tell anything about it, right? So, however, if you use fall curve, right, you can see, if I see the fall curve of the point before sensor change, this is the fall curve of the light sensor, is the fall curve of the temperature sensor, right? You can see there is two distinct fall curves, and I know, and hence I can automatically detect there was a sensor change, which means somebody interchanged a light sensor with a temperature sensor. Okay. Now, what happens is this is not the correct formula, right? You cannot apply the light sensor formula for all this data because there was a change here. So what you should do is up to 25, you apply the light sensor formula, and after 25 to 50 time units, you apply the temperature formula. So the plot would look like this now, right? That is up until this point, you have the illuminance data, and after that is the temperature data. Now you see this makes total sense, and to identify these, right, it's very hard without fall curves, right? Another example you can think is, imagine you have deployed this in an agricultural farm and you're asking the farmer to monitor these sensors, right? It is just impossible. And when, let's assume there was a fault in a sensor and you ask the farmer to replace the sensor, right? Then what happens is farmer doesn't understand where the sensor should go and how it should be connected, right? You would just connect wherever it just goes in, and that's when you will see these kind of issues. And the advantage of using our system, right, is that we can now automatically identify, oh, there was a sensor change, and we can automatically configure that this is temperature data, this is light data, right? You don't have to program the IoT device again, right? That's the key advantage. So that was predominantly the work on the fall curve, right? And I'm going to now talk about current sense. I'm going to pause here again to see if there is any questions up until now. Okay. No questions. If you have any questions, to raise hands or just ask me directly. Okay, let's go to the second fingerprint, right? So till now I was talking only about analog sensors, right, where you can measure the voltage directly. With digital sensors, you cannot do that directly, right? You cannot measure the voltage, analog voltage directly, right? So now let's see how we can detect faults in digital sensors. So the idea behind current sense fingerprint, right, is we monitor the current drawn by the sensor to derive a unique characteristic which differs between working and faulty. What I mean by that, right, is here is a pollution sensor and this is the current profile of the pollution sensor. Okay, this x-axis is time, y-axis is the current consumed by the sensor. As you can see, over time, there is a repeated pattern of the current consumption, right? This clearly shows there is a pattern of current being consumed by the device, right? This for a working sensor. Now, the key hypothesis what we have, right, is when a sensor component has a damage, right? Think of there is a broken component, there is a short circuit, any of these things, right? What happens is this sensor component damage also changes the physical properties of the sensor, right? Which again changes the current consumption. For example, let's say I have a faulty sensor and that current consumption looks like the orange line and the blue one is the current signature for a working sensor, right? Now, if you by just monitoring the current, right, I can now tell which is a working sensor, which is a faulty sensor. I don't even have to look at the sensor data, right? What is the pollution values? I don't even care about that, right? By just looking at the current signature, I can tell, oh, this is a working sensor, this is a faulty sensor, right? That's the key idea. For example, I can give you a simple analogy, right? Think of a refrigerator in our houses, right? Refrigerator consumes some amount of power, right? And basically, if you have a compressor, your compressor turns on, turns off, and you have a current signature very similar to this, for example, like much higher, definitely. But let's assume that your refrigerator has gone bad, which simply means it's no more drawing any power. And by just measuring the current, right, you can now determine whether your refrigerator is working or not, right? That's the same analogy here, but we are now doing it with sensors. Right? I will now explain how that fingerprint can be used, right? I'll take an example of air pollution monitoring. As we all know, right, air pollution is a major concern worldwide, especially in India, right, where we have 13 out of 20 most polluted cities in the world in India, right? And of course, this number is much more higher now with the recent surveys. To address air pollution, right, what people have been doing is they want to collect fine-grained spatio-temporal data at scale, right? So today what happens is, let me give you some context, right? Today what happens is government, right, has some air pollution devices across each city, right? For example, in Delhi, they have installed 40 locations where there is air pollution sensors, right, for the entire Delhi, right? For example, in Bangalore, there is 15 sensors for entire Bangalore, right, which is not sufficient, right? So if you want to identify potential sources like industry, households, which is actually eliminating too much or putting out too much pollution, right? You have to identify the sources. To do that, what you need is you have to deploy sensors everywhere, right? That's why people use low-cost sensors, which is $30 to $100, and people are now deploying at scale, right? For example, there is a lot of work in Switzerland, in Taipei, where there is thousands of sensors which is being deployed, right? And also in India, there is a lot of companies who are now deploying these sensors all across multiple cities. Okay. So the idea of these low-cost sensors is very simple. So here is a simple PM sensor. Okay. What it does, right? Let me give you a quick idea. That is, there is a small inlet and the outlet, right? And there is a fan. The fan keeps rotating inside the sensor, and airflow happens inside this chamber. Okay. And then there is a laser which is keep on beaming here, and if there is a particle, right, then it reflects, and that is measured by a photodiode, right? It's as simple as that. So basically, there is airflow, there is laser, and if there is any particles, it scatters the beam, which is measured by the photodiode and sends it to a microprocessor, right? That's the key idea. And now, if you think about this sensor, right, what can go bad in this sensor, right? If the fan, so there are two main components which can go bad. One is the fan, the other one is the laser, right? If the fan goes bad, there is no more airflow, right? So in those cases, either you will measure very high value or very low value, right? Because there is no more airflow happening inside the sensor. If the laser goes bad, then you're no more measuring or you're no more projecting the laser beam. So you'll be always measuring either very high value or very low value, right? So these are issues what can happen in the sensor. So let's understand that, right? So basically, in pollution sensors, the major components which can go bad, which causes garbage data, right, is because of fan and LED. Okay. So let's take an example. Okay. So here is two sensors. Red and the blue one is the pollution levels, right, between 0 to 60 over time. Okay. Time is here in minutes. As you can see, both are giving some pollution value, but one of them is a fan fault sensor, right? It's not easy to say which one is a fan fault sensor here, correct? However, I know the red one is the fan fault sensor, and the reason why it is behaving like this, right, is because there is no airflow, right? It is just measuring some arbitrary values, and that's why it is mimicking this data. Right? Here's another example, two sensors again, and one of these sensors has a LED fault, right? If you look at this data, you can see there are these spikes in the data, right? These spikes could be because of two reasons, right? One, it could be sensor has gone bad, which can be the case. Or imagine a scenario that this sensor is deployed next to the road, right? Where every time a vehicle passes, there is pollution data, right? It could be even because of that. So you have no way to tell which one of them is faulty, right? And then the third and the most important problem in these pollution sensors, right, is sensor drift. So let me explain that, right? So there are two sensors. Let's say the orange is a reference sensor and sensor 9 is the other sensor, right? So on day one, when I put these two sensors next to each other, you see both of the sensor data is very similar, right? Which is good. Now I take this sensor 9, deploy it in some other location for 1 month where there is high pollution data, okay? And then I bring it back to next to the reference sensor, and on day 30, right, if you see, the sensor 9 data is much higher than the reference sensor at the same location, right? This has happened because of wear and tear of the sensor, right? Because it was deployed in harsh conditions, the sensor has started wearing off, because of which you are seeing this difference in the data, right? So the key questions, what we are trying to ask here is, how can we detect and isolate faults in these sensors, right? Like, how can I tell which one is a fan fault, which one is a LED fault, right? And the second key question which we are trying to answer is, how can we detect there is a sensor drift, right? Because today, to detect sensor drift, you have to bring back the sensor to the original location, which is not feasible, right? Imagine you're deploying it in Delhi and then you have to bring it all the way back to Bangalore to check whether the sensor is working. It doesn't work, right? But these are the challenges what IoT community is facing today in terms of this low-cost deployment, right? Now, let's see how current sense can identify or help solving those problems, right? So the first key property of current sense, right, is it can distinguish between a working and faulty sensor. What does it mean? So here is a working sensor's current signature, right? This is the current signature of a working sensor. S1 indicates, so basically what happens in the sensor is, when you turn on the sensor, your fan turns on. So you see the current consumption at 40, right, is typically the fan current consumption. And then periodically LED turns on, that's why you see the S2, right? Basically, that's the operation of the sensor. Now, imagine the fan has gone faulty, right? Now, the current consumption, you see, it has dropped down to less than 20 as opposed to 40, which can clearly say that there is a fan fault, right? But still there is a spike which indicates the LED is working correctly, right? Assume the LED is faulty, that is the green one. You can see that there is no more spikes in the data, which indicates the LED is faulty, right? And then let's say both LED and fan have become faulty, right? In such scenario, you would see a red line, which is simply saying there is very low current consumption by the device, right? The key summary is that by just measuring current, you can now detect it's a working or fan fault or laser fault, or is it completely faulty. That's the key property. The second property, right, is it is independent of the measured phenomenon, right? What it means is, here are two sensors, okay? One sensor, which is sensor A, sensor 17 deployed in environment A, the blue sensor, right? It is deployed in environment A, which is basically very dusty, which has very high pollution values and also high temperature. The outside temperature is very high, okay? And then there is environment B, which is low temperature, and it is a clean environment, right? And you can see the current consumption of both these sensors is not changed at all, right? Because all we are measuring is current, not the PM data, right? That's the reason why the current signatures are independent of where it is deployed, which means once I collect a fingerprint, right, then the same fingerprint will be remaining on the device for its lifetime. The third property, right, is, does this fingerprint remain the same across all pollution sensors, right? So if I take a pollution sensor from the same manufacturer, right, these are 5 pollution sensors from the same manufacturer, all of them you see have very similar signatures. However, if I take two different manufacturers, right? Like the blue one is a plant tower sensor from China, the orange one is a Sensorion sensor from the US. You can see these two have two different signatures, and now, just like before, we can now also determine first, is it a pollution sensor, and then we can also say from which manufacturer is a pollution sensor. Okay. So that's the current signature, right? So basically, what we told you till now is that we can now detect whether current signatures can detect whether there is a fault or not, right? And now, to use this current signatures accurately, right, what we do is we transform the current data to FFT features, right? So the top two graphs here shows the current data, and we convert this current data to FFT features. Okay, and now fingerprint. Hello, is there a question? Okay. So now basically fingerprint is nothing but combination of these FFT features for both the fan component and also the LED component, right? So this is what the fingerprint would look like. So before we answer how accurate it is and stuff, right? First question is, how do you measure current, right? So typical IoT devices generally has a current monitoring circuit, right? And it is very low cost, less than $1. It can measure all the way from 10 microampere to 10 amperes, right? And it's very precise with errors less than 1%, right? So people use this in their IoT devices today to measure their batteries and things like that, right? So first scenario is, if a device already has a current sense amplifier, right? All we need is just a software code to measure the current, right? Imagine a scenario that your device does not have a current sense amplifier, right? In that scenario, what we do is we have designed a small PCB which measures the current. So this is the current sense amplifier which measures the current, right? So now you can attach this PCB to any sensor so that you will get to know what is the current consumption. So let me talk about the deployment of such a system, right? So we partnered with one of the startups who has deployed over 200 plus air pollution sensors, such as these, right, all across India. Okay. Now, one of the problems what they had, right, is take this location here, right, somewhere in Lucknow, you're getting very high value of 229 pollution values. The question, right, is this correct data, faulty data? What's actually happening, right? Especially imagine if the government or policymakers is looking at this data, right, they have to take decisions, and that is not clear by just looking at this data, right? What we have done is we had a deployment in Bangalore where we deployed over 51 pollution sensors, right, for 8 months period. Okay, and the scenario was that we collected data every 1 minute along with its fingerprint. Okay. To collect the ground truth, what we did is every week there was a person who went to each of the sensors in Bangalore and identified whether it's working or faulty. Okay, so in total of 51 sensors at the end of 8 months, right, we had around 20 sensors which was faulty. Okay, now let's see how we can detect faults using current. So here is again PM data over time for two sensors, and it is basically pollution sensors, right? If you look at the data, they both look pretty similar, right? It's very hard to say whether is there a fault or not. However, at this scenario, at this time period, right, sensor orange, that is sensor 32, has a fault. So if I look at the sensor 32's FFT features, right, if I look at FFT feature at 30 Hertz, you can see sensor 32 before this point, after this point, they have very similar signature, which means there is no fault in LED component, right? However, if you look the FFT features at 5 kilohertz signal, which is for fan, you can see the fan signal is kind of completely distinct compared to before, which indicates that there is a fan fault in this scenario, right? So without any contextual information or without any sensor redundancy, right, we can now use current sense to detect and isolate the fault. How does this approach compare with data-centric algorithms, right? So we have compared our work with the standard anomaly detection, right? And basically what does anomaly detection mean is, one, you can have spatial anomaly, right? That is, imagine to identify a spatial anomaly, right, I will see, is my sensor data higher or lower than any other sensor nearby me, right? If it is, then I make it as an anomaly, right? This is spatial anomaly. That is, if my data is higher than nearby sensor data, then it is spatial anomaly. Temporal anomaly means for the same device, if I have seen, if the data is significantly varying compared to yesterday, right, then I detect it as a temporal anomaly, as an example. Spatial temporal anomaly means, yes, there is both spatial anomaly and temporal anomaly. That's why it's a spatial temporal anomaly, right? And now if you look at the accuracies, you can see F1 score is of, if I just look at spatial anomaly, it is of 77%. The reason because of this low F1 score is, as I said, pollution is very dynamic, right? It is hyper local. That is, let's say you are sitting it, you are deployed a sensor in one of the road intersect in one location, right? As I showed you in the previous scenario, if because of the local variations, that there could be a vehicles going on, there could be some factory turning on their machinery, whatever be the case, right? Because of local variations, just relying on spatial anomaly, you cannot tell whether the sensor is working or faulty. The second scenario, right, is temporal anomaly, where we look at historical data, right, to detect faults. And in that case, again, the accuracy is very low because imagine you have deployed a sensor in the intersection of a road. Okay, based on traffic, right, your pollution data also changes. Let's assume yesterday there was no traffic, it was a weekend, right? Your pollution data is very low, and if you use that data to detect anomaly for the next day, then your value will be very low because pollution is is non-stationary, right? Because of varying emission sources. Hence, again, this won't work. And if you use both, again, that accuracy is very low, right? Now let's see how using current sense we can improve the accuracies, right? What we have done again is we have created a small ML algorithm which will classify each sensor as either working, or it has a LED fault or a fan fault or completely faulty, right? So we collect training data for each class of faults, right? And basically before you deploy the sensor, we use two working, one faulty, one fan fault, one laser fault, one completely faulty, right? We collect training data, we build a model, and our model has 99% accuracy to do 4-class classification. Okay. Now what we have done is we have taken this ML model which we deployed, which we developed in the lab, right? We deployed it in all the 51 sensors in Bangalore. Okay, and then for 8 months we evaluated how does this model perform, right? Our model has over 98% accuracy in detecting faults. What does it mean? So here is the precision recall for each class, right? That is, let's take working class. We are able to say with 99% accuracy this sensor is working or not, right? Similarly, we can say with 98, 97% accuracy whether a sensor has a fan fault or a laser fault or completely faulty. Okay, and here is the confusion matrix for working fan fault, laser fault, completely faulty. As you can see, the diagonal elements have very high values, which means the accuracy is very high, and there is very little false positives, right? Which means even though there is no fault, but we are saying there's a fault, so they are very low, right? Which simply indicates the efficacy of the algorithm which is designed to detect whether there is a fault or not. Okay. So now, again, I'll pause here for a minute to see if there's any questions. Do you have any questions, anyone? Okay, I'll continue. So now let's look at, so that was sensor fault detection, right? Now let's look at how do we detect sensor drift, right? Sensor drift, first of all, occurs when one or more components of the sensor has changed its properties, right? This could be either due to wear and tear or because of degradation of the components, right? And this sensor drift can go unnoticed for long periods if you don't put it back in the co-location, right? That is, imagine you deployed a sensor in some remote location. Because of wear and tear, the sensor could have drifted, right? You will never notice the sensor drift unless you either calibrate them or you just put them next to a reference sensor, right? And that is very bad. And this is the example which I showed you, right? On day 1, both the sensors had similar data. On day 30, you see sensor 9 has now changed the data completely, right? The key question is, how do we detect this? Once the sensors are deployed in the field, how can we detect this and how can we solve this problem, right? So the way to solve this, right, is based on this key intuition that whenever there is a change in fan speed, or so what does sensor drift mean, right? As I told you, sensor drift means that there is some change in the sensor components, right? In this case, the change could be either fan speed has reduced because of dust, or it could be LED intensity has reduced because of wear and tear, right? When either of these occurs, it also changes the current consumption, right? We can now measure the current and then tell whether there was a change, and which implies there is a change in the pollution data. So in other words, right, here is a simple graph which says the x-axis is basically change in current consumption, okay, which on the dominant frequency, and y-axis is change in PM data, right? If there is no change in any of the components, then your PM data should be same, okay. However, if your current consumption decreases by 20% here, right, then your pollution data also decreases by 25%. So there is a clear correlation that if my current consumption increases, my PM data, which is pollution data, also increases. If the current consumption decreases, the pollution data also decreases, right? We can now use this correlation to determine, is there a drift, first of all, and can we compensate for that, right? So what we have done is we identified there were 9 sensors which had sensor drift, okay? And in these 9 sensors, we looked at the PM RMSE errors. And as you can see, there is very high RMSE errors, close to 16 across all these sensors, right? And then after using current sense and after we automatically calibrate these sensors, right, we can reduce the RMSE error by less than 3, right? Which is over 86% reduction in average error across all the 9 sensors, right? Thus, we can use these fingerprints also to detect sensor drift, right? So both sensor fault and sensor drift are one of the most common problems in any IoT devices, in any IoT deployments, okay? Now the question is, okay, till now we were talking about one sensor, right? Can this signature work for other pollution sensors, right? So here is one sensor from Sensorio and the other one from Honeywell, right? And if you look at this, you see the current consumption of a working and a faulty are 2 different things. So we can use that efficiently to detect faults in this sensor. Similarly, for Honeywell sensors also, right? You see, this is the PM data, right? And this is the current. You can see the faulty one, which is in red, which is completely different than the working one, right? So across any pollution sensor, if we just measure current, right, we can now detect whether this is working sensor or a faulty sensor. Okay. The next slide basically tells, can this current signature work with other sensor types, right? That is not pollution, but it could be something else, right? So here is an example. Here is a carbon dioxide sensor, right? And this is the data from the 2 sensors. As you can see, both working in blue and faulty in orange, they have similar data, right? Again, you cannot tell which one is faulty or not. However, if I measure the current of the sensor, right, you can see blue one is the working sensor, green one is the drifted sensor. You can see drift has reduced the current consumption, and orange is the faulty sensor, which is completely different, right? So by measuring current, we can detect faults in any type of sensor, right? In this case, it's a CO2 sensor. Here's another example of a multi-gas sensor, right, where we have current signature for working one, which is here, and here is the current signature of a faulty one, right? So by just measuring current, you can now detect whether it's a working sensor or faulty sensor, or does it have a bit drift, right? So that's the key set of points which I wanted to make in this talk. And to conclude the talk, right, what I have presented here is basically a novel state-of-the-art approach, right, to detect and isolate faults using 2 fingerprints called fault curve and current sense, right? And the key property is that each of these fingerprint has a unique signature, right, and it is agnostic to the phenomenon being monitored, right? And we have over 95% accuracy in detecting sensor faults with very nominal energy overhead, right? And to measure these fingerprints, you don't need any additional hardware modification to do that, right? So all using just software, we can now design reliable IoT devices, right? And the objective of doing that is you want to provide users reliable, high fidelity IoT data, right? So that they can make decisions. And this could be for any domain, right? It could be in agriculture where farmer has to take a decision based on soil moisture data. It could be in aircraft where an automated system has to control the temperature. It could be in self-driving vehicles where you're getting, for example, some LiDAR data, right? How do you know that data is valid or not before you stop the vehicle or accelerate, right? So across every domains where IoT devices and sensors are deployed, it is very important to ensure the quality of the data, right? As part of the future work, what we are doing is that we are trying to create standards, right? Which says every time you collect data, there should be some kind of a fidelity parameter, right? Which should be associated so that anyone who consumes the data knows whether it's valid data or faulty data, right? And another interesting thing what we are trying to do is, as I mentioned, today people resort to expensive sensors because they don't want the sensor to go bad, right? And if they go bad, then you have to spend more money to send somebody to fix it, right? One idea is, let's say I am deploying 10,000 rupees sensor, right, in one location, right? And let's assume that's lifetime is 5 years. Now the question which we are trying to answer, right, is can I replace the 10,000 rupees sensor with 500 rupees sensors, right? And I just use one 500 rupees sensor every time so that since I now can monitor the health of the sensor, right? If one sensor goes bad, I can switch to the next one, right? So the overall cost of the sensor will completely come down and also increase the overall lifetime, right? So that's another future work which we are looking at, right? So that's the broad overview of how do you improve data quality in IoT devices, right? And in this talk, basically, I covered one, how do you detect faults, how do you isolate faults, how do you detect sensor drift, and I showed you with multiple examples in agriculture and environment monitoring, right? With that, I'll conclude my talk and I'll stop here. If you have any questions, write to me or you can visit my website for more details. And if you have any questions now, I'm happy to answer. Yeah, sure. So one question is on can I elaborate on the algorithms that is used for fault cover analysis, right? So that's a good question. So what we are doing, just going back there, right? To give you a bit more details. Yeah. So what we do, right, is as you remember, fault curve is basically exponential curve, right? What we do is we extract features for each of the curve, right? Specifically, we basically do a polynomial curve fitting, right, for each of the curve, and all the coefficients, right, becomes the features, right? So if it's a capacitive sensor, it will have its features. We'll fit the polynomial curve, we'll get the features. If it's a resistive sensor, again we'll fit the curve and then get the features, right? So for each sensor, we fit the polynomial curve, get the features, and create a database like this, right? Because in IoT device for a particular deployment, right? Take agriculture as an example. There are at most 10 sensors what you can use, right? So this database will contain 10 sensors along with their features. Okay. Now that is one-time activity. You create this database and you store it in your IoT device. In the field, right, what we do is we do a simple nearest neighbor search. That is, I extract the fault curve, right, and I again fit the polynomial curve for the fault curve. I get the features. Now I compare these features with the database features, and whichever has the nearest distance, right, I then say that is the fingerprint it should match to, right? For example, let's assume it's a temperature sensor, right, and it's a working temperature sensor, okay? Then what happens is the working temperature sensor should match with the temperature sensor features in the database. If it does not match, then there was no nearest neighbor match, and hence we detect that as faulty, right? So the key idea is if there is a match, it is a working sensor. If there is no match, then it is not a working sensor, right? By just using a simple KNN algorithm, we can now detect with a very high accuracy. Does that answer your question? Okay, any other questions?
Participants, if you have any questions, you can come out with your question, or even you can type your questions in chat box.
Right. So the second question is, which tool did we use for this analysis? So this all the algorithms what we have developed, right, is all open source, right? So specifically, there is a library which we have released called EdgeML, which is basically as both Python and C code variants. So that's the code and the tool chain what we have used. So I suggest everyone to just search for EdgeML and Microsoft, right? You should be able to find the GitHub repository which has these algorithms. And as I mentioned, one of the key ideas of these algorithms is that you can run them on resource-constrained IoT devices, even such as Arduino, right, which has just 2 KB of flash, right? So that's the tool which we use.
Any other questions from participants?
What are the So the next question is, what are the parameters we should measure for IoT devices? Are you talking about um, for detecting faults, or is this something else? Okay. So yeah, so for our analysis, right, we focus predominantly on electrical characteristics, namely the current and voltage, right? Those are the So if you think of a typical IoT device, right, what you can measure is broadly just current and voltage, right, apart from data, right? So as I told in the beginning of my talk, if you just measure data, it's not sufficient to tell whether there is a fault or not, right? So what we do is we go beyond data, right? What we try to do at the high level, right, is we understand the physics of the sensor, right? How does the sensor work? Why does it work this way, right? Why does the current change? So that's the whole idea of the entire work, right? So what we do measure is basically current and voltage, right? And the takeaway from this talk, what you should get is that by measuring current and voltage, there is a lot of information which can be used to detect faults, drift, or any other scenarios, right? That's a key takeaway message. Yeah, the tool name is called EdgeML algorithms. So just search for EdgeML and Microsoft. You should be able to get that. Okay, if there is no more question, then do you think we should wrap up the session?
Just, shall we close the session, sir?
Yeah, if there are no more questions, then we could close it.
Yes, yes, sir. There are no questions from participants.
Okay then.
Understand?
Yeah, thank you for the opportunity, and I think it was nice talking to you all. And as I said, if there is any questions later on, or if any of you are interested in the projects what we are working at Microsoft Research, please reach out to me for opportunities. Thank you.
Sir. So on behalf of our department and my own behalf, I extend a sincere thanks to our speaker, Mr. AkshayNambi from Microsoft Research, for giving valuable insights on dependable IoT, improving IoT sensor data quality through robust sensing. So I am sure your address will help a lot in understanding the concepts of IoT, sir. Thank you, sir. Thank you for accepting our invitation.
Thank you.
Thank you, sir.
Thank
you, sir.
you.
Dear participants, feedback form and attendance form is posted in chat box. Please fill the form before you leave the session. So next session starts by 2 p.m. You can have your lunch and you can log in exactly at 1:45 p.m. for the next session. Thank you.
Job consolidation master culture.
Participants, please check, can you able to access the form now? Okay, thank you. Thank you, sir. Thank you.
ಕರೆಕ್ಟಾಗಿದೆ ಮಾಡಪ್ಪ. ಆ ಮೀಟ್ರ್ ಕೂಡ ಅಷ್ಟೇ ತೆಗ್ದಾಕಿಲ್ಲಿ ಕೂಡ. ಈಗ ಎಫ್ ಇಂದ ಇಲ್ಲಿ ಕೂಡ ಆ ಮೀಟ್ರಿಗೆ ಇಲ್ಲಿ ಕೂಡ ಇಲ್ಲಿಂದ ಆ ಎಫ್. One voltmeter connected across DC supply. ಪ್ಲಸ್ ನೋಡಿದ್ರ ನೋಡಿದ ತಕ್ಷಣ ಟ್ರೈ ಅಷ್ಟೇ ಕರೆಕ್ಟಾಗಿದೆ. ಹೊರಡಿ ಅಲ್ಲಿ ಕಟ್ ಸೆಕ್ಷನ್ ನೋಡ್ಕೊಂಡು ಅಲ್ಲಿಗೆ ಹೋಗಿ. ಹಿಂಗೆ ಇರಲಿ. ಅವೆರಡು ಜೀರೋ ಇದ್ರೆ ನೋ ಲೋಡ್ ಅಂತ. ಆಮೇಲೆ ನೀವು ಅಪ್ಲೈ ಮಾಡ್ದಂಗೆ ಒಂದು ಕಣಪ್ಪ, ಒಂದು ಕೊಡ್ತಾರೆ. ಇವ್ರೇನು ಎರಡೇ ಕೊಟ್ಟರು ರಘುನಾಥ್ ಸರ್. ಒಂದೇನೆ ಈಗ ನಾವು ಬೇರೆ ಬ್ಯಾಚ್ಗೆಲ್ಲ ಒಂದೊಂದು ಕೊಟ್ಟಿದ್ದೀವಿ.
ಸರ್ ಅದು ಮಾಡೋಷ್ಟರಲ್ಲಿ ಆಗುತ್ತೆ ನಮಗೆ. ಪ್ರೊಸೀಜರ್ ಎಲ್ಲ ಬರೀಬೇಕು.
ಒಂದೊಂದನೇ ಕೊಡಿ ಅಂತ ಹೇಳ ಪಾಪ.
ಆಮೇಲೆ ರೆಕಾರ್ಡ್ ಬೇರೆ ಬರಬೇಕು.
ಗೊತ್ತಾಗ್ತಾ ಇದೆ ನಮಗೂ. ಬಟ್ ಏನೀಗ ನೀವು ಇಂಟರ್ನಲ್ಸ್ ಬರೆದ್ರೆ ಮುಗೀತು ಕಣಪ್ಪ ನಿಮ್ಮದು. ಏನು ಮೇನ್ ಎಕ್ಸಾಮ್ಗೆ ಏನು ತಂದ್ರೆ ತಗೊಳ್ಳಿ. ಸುಮ್ಮನೆ ಬರೆದ್ಬಿಟ್ಟು ಒಳಗಡೆಗೆ ಬಂದರೆ ಯಾವಾಗ ಬೇಕಾದರೂ ಬನ್ನಿ, ನೀವು ಮಾಡಿಸ್ಕೊಡ್ತೀನಿ. ಹಾಂ, ಡೆಮಾನ್ಸ್ಟ್ರೇಷನ್ ಹಂಗೆ ಕೇಳ್ತಾರೆ. ಕಾಮ್ಯುಟೇಟರ್ ಅಂದ್ರೇನು, ಪೋಲ್ಸ್ ಅಂದ್ರೇನು, ಪೋಲ್ ಕೋರ್ ಅಂದ್ರೇನು, ವೈವಾ ಕೇಳ್ತಾರೆ. ಪೋಲ್ ಕೋರ್ ಅಂದ್ರೇನು, ಈಗ ನಿಮ್ಗೆ ಯಾವ ಎಕ್ಸ್ಪೆರಿಮೆಂಟ್ ಬಂದಿರ್ತದೆ ಅದ್ರ ಮೇಲೆ ಕೇಳ್ತೀವಿ. ಈಗ ಡೆಮಾನ್ಸ್ಟ್ರೇಷನ್ ಮೇಲೆ ಅದನ್ನೇ ಕೇಳ್ತೀವಿ ಕಣಪ್ಪ. ಕಾಮ್ಯುಟೇಟರ್ ಅಂದ್ರೇನು, ಪೋಲ್ ಕೋರ್ ಅಂದ್ರೇನು, ಪೋಲ್ ಶೋ ಅಂದ್ರೇನು, AC ಮೋಟ್ರ್ ಅಂದ್ರೇನು, DC ಮೋಟ್ರ್ ಅಂದ್ರೇನು, ಡಿಫ್ರೆನ್ಸ್ ಕೇಳ್ಕೊಂಡು ಹೋಗ್ತೀವಿ ಅಷ್ಟೇ. ಏನು ನಿಮಗೆಲ್ಲ ಏನು ಅಂತ ಡೀಪ್ ಆಗಿ ಹೋಗಲ್ಲ, ಬೇಸಿಕ್ಕು ಎಲ್ಲ. ಹಾಂ, ತಗೊಳ್ರಪ್ಪ. ಅಲ್ಲಿ ಕ್ರಾಸ್ ಕನೆಕ್ಷನ್ ನೋಡಿಕೊಂಡು ಆಮೇಲಿಂದ ಹೋಗಿ ಮಾಡಿ, ನಿಮ್ಮ ಪಾಡು ನೀವು ಮಾಡಿ. ಸರಿಯಾಗಿದೆ ಕಣಪ್ಪ. ಫೋಟೋ ಹೊಡ್ಕೊಳ್ಳಿ ಬೇಕಾದ್ರೆ ಒಂದು ತಗೊಂಬಪ್ಪ. ಅಲ್ಲಿ ಆ ಕ್ಲಾಸ್ ರೂಮಲ್ಲಿ ಆಯ್ತಾ? ಬೇಡ ಬಿಡಿ, ಇವರೇ ಶೇರ್ ಮಾಡ್ತಾರಂತ ಹೇಳಿದ್ದೀನಿ, ನಿಮ್ಮ ಗ್ರೂಪ್ಗೆ ಹೇಳಿದ್ದೀನಿ. ಗೊತ್ತಾಯ್ತಲ್ಲ ಈಗ. ಯಾರು ಎಕ್ಸಾಮ್ಗೆ ಟೆನ್ಷನ್ ಮಾಡ್ಕೊಂಡು ಬರೋಕ್ಕೆ ಹೋಗ್ಬೇಡ. ಈಸಿ ಇರ್ತೈತೆ ಕ್ವಶನ್ಸ್ಗಳು. ಏನು ಏಮು, ಆಪ್ರೇಟರ್ಸ್ ಅವೆಲ್ಲ ನೋಡ್ಕೊಂಬಂದಿರಿ, ಬರೀತೀರಾ. ಅದಾದಮೇಲೆ ಕಂಡಕ್ಷನ್ ನಾವು ಮಾಡಿಸ್ಬೋದು. ನಾವು ಬರ್ತೀವಿ, ನಾನೇ ಬರ್ತೀನಿ, ಬಂದು ನೋಡ್ಬಿಟ್ಟು ಇದು ಮಾಡ್ತೀನಿ. ಜಾಸ್ತಿ ಟೆನ್ಷನ್ ಮಾಡ್ಕೊಳ್ಳೋಕ್ಕೋದೇನು ಬೇಡ ಕಣಪ್ಪ. ಏನು ಇವೆಲ್ಲ ಸಿಂಪಲ್. ಸ್ಟಾರ್ಟು ನೀವು ಫುಲ್ಲು ನೋಡಿ ಈ ಥರ. ಈಗ ಅಲ್ಲಿ ಆನ್ ಮಾಡಿ ಹೇಳಿ ತೋರಿಸ್ತೀನಿ. ತ್ರೀ ನೋಡಿ ಈ ಥರ. ಇಲ್ಲ, ಅದು ಮ್ಯಾಗ್ನೆಟೈಸ್ ಆಗಿಲ್ಲ. ಈಗ ಆಯ್ತು ನೋಡಿ. ಇಲ್ಲೇ ಆಫ್ ಮಾಡ್ತೀವಿ, ಬೇಡ. ಇದು ಆನ್ ಆದ್ಮೇಲೆ ನೀನು ಸ್ಟಾರ್ಟ್ ಮಾಡ್ಬೇಕಲ್ವಾ. ಇದನ್ನಾದ್ರು ಮೋಟ್ರ್ ಹೆಂಗ ಏನಾಗ್ತದೆ ಏನಪ್ಪ? ಡಿಮ್ಯಾಗ್ನೆಟೈಸ್ ಆಗ್ಬೇಕಲ್ಲಪ್ಪ. ಇದು ಮ್ಯಾಗ್ನೆಟೈಸ್ ಆಗ್ಬೇಕಲ್ವಾ. ಮ್ಯಾಗ್ನೆಟೈಸ್ ಪವರ್ ಇಲ್ದಾನೆ ಹೆಂಗೆ ಮ್ಯಾಗ್ನೆಟೈಸ್ ಆಯ್ತದೆ? ಆಗಲ್ಲ. ಅದಕ್ಕೆ ನಾವು ಆನ್ ಮಾಡಿಬಿಟ್ಟೆ ಸ್ಟಾರ್ಟ್ ಮಾಡ್ಬೇಕು. ಗೊತ್ತಾಯ್ತಪ್ಪ. ಈಗ ಅಲ್ಲಿ ಕಟ್ ಸೆಕ್ಷನ್ ನೋಡ್ಕೊಳ್ಳಿ. ಕಟ್ ಸೆಕ್ಷನ್ ನೋಡ್ಕೊಂಡು ಅಲ್ಲಿಗೆ ಹೋಗಿ. ಗೊತ್ತಾಯ್ತದಲ್ವ ಕಟ್ ಸೆಕ್ಷನ್ನು? ನೋಡ್ಕೊಂಡು ಹೋಗಿ ಅಲ್ಲಿ.
ಇನ್ಪುಟ್
ಹ್ಞೂ
ಇನ್ಪುಟ್ ಆದ್ಮೇಲೆ ಔಟ್ಪುಟ್ ಇಂದ ಇನ್ಕ್ಯಾಂಡಿಸೆಂಟ್ ಬರುತ್ತೆ.
ಯಾವ್ದಾರು ಕೊಡ್ಬೋದು. ಹೌದು
ಇನ್ಕ್ಯಾಂಡಿಸೆಂಟ್ ಔಟ್ಪುಟ್.
ನೋಡಪ್ಪ, ಈ 2 ಇನ್ಪುಟ್ನ ಈ ಇನ್ಪುಟ್ ಕೊಡಪ್ಪ, ಈ 2 ಔಟ್ಪುಟ್ನ ಈ 2.
ಇದು ಯೂಸ್ ಇಲ್ವಾ?
ಇದು ಯಾಕೆ ಯೂಸ್ ಮಾಡ್ತೀಯಾ? ಇದು ಪವರ್ ಮೆಜರ್ಮೆಂಟ್ ತಾನೆ. ಇದು 2 ವೇ ಕಂಟ್ರೋಲ್ ಮೆಥಡ್, 3 ವೇ ಕಂಟ್ರೋಲ್ ಮೆಥಡ್ಗೆ ಇದು. ಹೌದು,
ಇದು 2 3 ಇದ್ರಲ್ಲಿ ಮಾಡ್ಬೋದಾ ನಾವು?
ಸರ್
ಎರಡಕ್ಕೂ ಒಂದೇ ಟೇಬಲ್. ಫಸ್ಟು LED ಮಾಡ್ತೀಯಾ, ಆಮೇಲೆ ಇನ್ಕ್ಯಾಂಡಿಸೆಂಟು, ಆಮೇಲಿಂದ ಫ್ಲೋರಸೆಂಟು.
ಕಾಂಬಿನೇಷನ್
ಇದೆರಡು ಕಾಂಬಿನೇಷನ್, ತಿರ್ಗಾ ಇದೆರಡು ಕಾಂಬಿನೇಷನ್ ಮಾಡ್ತೀಯ, 3 ಕಾಂಬಿನೇಷನ್ ಮಾಡ್ತೀವಿ. ಹಾಕ್ಕೊಡ್ತೀವಿ, ನೀನು ಮಾಡ್ತೀನಿ. ಹಾಂ ಸರಿ, ಅಲ್ಲಿ ಕಟ್ ಸೆಕ್ಷನ್ ನೋಡ್ಕೊಂಡು ಹೋಯ್ತಾ? ಕಟ್ ಸೆಕ್ಷನ್ ಇದೆ ಮೋಟ್ರದ್ದು, AC DC ಮೋಟ್ರ್. ಆ ಸೈಡು ಟೇಬಲ್ ಮೇಲೆ ಇದೆ,
ನೋಡ್ಕೊಂಡು
4 ಅಪ್ ಅಲ್ಲಿಗೆ. ಯಾರಿಗಾದ್ರೂ ಡೌಟ್ಸ್ ಇದ್ರೆ ರಿಪಿಟೇಷನ್ ಏನೋ ಮಾಡ್ಕೋತಾ ಇರಿ, ಅಲ್ಲಿ ಬರ್ತೀನಿ ನಾನು, ಅಲ್ಲಿ ಜಾಯ್ನ್ ಆಯ್ತೀನಿ. ಸರಿ, DC ಶಂಟ್ ಮೋಟ್ರ್ ತೆಗಿಯೋ.
ಲಾಸ್ಟ್ ಯಾರು ತೆಗ್ದಿದ್ದು?
ಅವನು 2 ಅಡ್ಮಿಟರ್ಸ್ ಮಾತಾಡ್ತಿದ್ದಿಲ್ಲ. ಆಯ್ತಾ, ನೋಡಿ ಈಗ ಸರ್ಕ್ಯೂಟ್ ಡಯಾಗ್ರಾಮ್ ಇಲ್ಲಪ್ಪ, ಅದು ಇದು ನೋಡಿ, ಇದು ಕಣ. ಈಗ ಇದ್ರಲ್ಲಿ ನೋಡಪ್ಪ, ಇಲ್ಲಿ ಡಿ ಸಿ ಇಟ್ ಮೀನ್ಸ್ ಪಾಸಿಟಿವ್ ನೆಗೆಟಿವ್ ಅಂತ ಬರ್ತೈತೆ ಇದರಲ್ಲಿ. ಈಗ ನಾವು ಪಾಸಿಟಿವ್ ಇಂದ ಸ್ಟಾರ್ಟ್ ಮಾಡ್ತೀವಿ ಕನೆಕ್ಷನ್ನು. ಪಾಸಿಟಿವ್ ಇಂದ ಒಂದು ಎಲ್ಲಿಗೆ ಹೋಗಿದೆ ಹೇಳಪ್ಪ ನೀನು? ಆಮೀಟರ್ಗೆ ಹೋಗಿದೆಯಲ್ಲ, ಒಂದು ಆಮೀಟರ್ ಕನೆಕ್ಟ್ ಮಾಡಿ. ಅದರ್ ಎಂಡ್ ಆಫ್ ದ ಆಮೀಟರ್ ಕನೆಕ್ಟೆಡ್ ಟು ಎಲ್ ಆಫ್ ದ ಸ್ಟಾರ್ಟರ್. LAF ಅಂದರೆ ಲೈನು, ಆರ್ಮೇಚರು, ಫೀಲ್ಡ್ ಅಂತ. ಸ್ಟಾರ್ಟರ್ದು LAF ಅಂದರೆ. ನೆಕ್ಸ್ಟು ಎ ಇಂದ ಡೈರೆಕ್ಟ್ ಆಗಿ ಮೋಟರ್ ಎ ಇಂದ ಮೋಟರ್
LAF ಅದಾಗದೇ ಕನೆಕ್ಟ್ ಆಗಿರುತ್ತೆ.
ಹ್ಞೂ ಹೌದು, ಇಂಟರ್ನಲ್ಲಿ ಕನೆಕ್ಟೆಡ್, ಅದು ಇಂಟರ್ನಲ್ಲಿ ಕನೆಕ್ಟೆಡ್. ನಾವು ಈಗ ಎಲ್ಲಿ ಕನೆಕ್ಟ್ ಮಾಡ್ದು, ತಿರ್ಗಾ ಎ ಇಂದ ಎಲ್ಲಿ ಕನೆಕ್ಟ್ ಮಾಡ್ತೀವಿ? ಎಗೆ ಕನೆಕ್ಟ್ ಮಾಡ್ತೀವಿ, ಇಲ್ಲಿಗೆ. ಎ ಇಂದ ಎಗೆ ಕನೆಕ್ಟ್ ಮಾಡ್ದು, ಆಯ್ತಾ? ನೆಕ್ಸ್ಟು ಎ ಇಂದ ಫೀಲ್ಡ್ FFಗೆ ನೋಡಿ, ಇದು ಫೀಲ್ಡ್ FF. ಎ ಇಂದ ಫೀಲ್ಡ್ FF, ಆಯ್ತಾ? ಈ ಪಾಯಿಂಟ್ಗೆ ಬಂತಾ ನೋಡಿ, ಇಲ್ಲಿ ಬಂದು ಈಗ. ನೆಕ್ಸ್ಟ್ FF ಇಂದ, ಅದೇ ZZ FF ಅದು. ಆ FF ಫೀಲ್ಡ್ ಇಂದ ನೆಗೆಟಿವ್ ಹೋಗ್ತಾ ಇಲ್ಲಿಗೆ ಕಣ, ಇಲ್ಲಿಗೆ ನೆಗೆಟಿವ್ ಆಫ್ ದ ಸಪ್ಲೈ. ಇಲ್ಲಿ ಬಂತಾ? ಈಗ F ಇಂದ ಒಂದು ಫೀಲ್ಡ್ ಆಮೀಟರ್ ಕೊಡಿ IFಗೆ, ಆಯ್ತಾ? ಅವೆರಡು ಆಮೀಟರ್ನೇ. ಈ ಆಮೀಟರ್ ಇಂದ F ಕೊಟ್ರೆ ಮುಗೀತು ನಿಮ್ದು ಕನೆಕ್ಷನ್ನು.
ವೋಲ್ಟ್ ಮೀಟರ್
ಒಂದು ಅಕ್ರಾಸ್ ಒಂದು ವೋಲ್ಟ್ ಮೀಟರ್ನ ವೋಲ್ಟೇಜ್ಗೆ ಕೊಡಿ. ನೋಡಿ, ಇಷ್ಟೇ ಮುಗೀತು, ಇಷ್ಟೇ ಕಣ. ಗೊತ್ತಾಯ್ತದೆ, ಆಯ್ತಾ? ಈಗ ಅಲ್ಲಿ 5 ಆನ್ ಮಾಡ್ಬಂದು 5 ಆನ್ ಆಗಿದೆ. ಎಂ ಮೋಟರು, DC ಶಂಟ್ ಮೋಟರ್. ಇದು ಮೋಟರು, ಆಯ್ತಾ? ಇದು ಫೀಲ್ಡು, ಮೋಟ್ರದ್ದು ಫೀಲ್ಡ್. ಇದು ಆರ್ಮೇಚರ್. ಗೊತ್ತಾಯ್ತು ಈಗ? ಇದು ಇದು ಇಲ್ಲ, ಇದು ಸ್ಲಿಪ್ಪು. ಅಲ್ಲಿ ಮಾಡಲಿಲ್ಲ ನೀವು ಇದನ್ನ, ಸ್ಲಿಪ್ಪು, ಆಯ್ತಾ? ಇದಕ್ಕೇನಂತೀವಿ ನಾವು? ಸ್ಪ್ರಿಂಗ್ ಬ್ಯಾಲೆನ್ಸ್. ಹಾಂ, ಸ್ಲಿಪ್ಪು. ಸ್ಲಿಪ್ಪರ್ ಅಂದ್ಯಾ ಅಲ್ಲಿ, ಆಯ್ತಾ? ಇದರಲ್ಲಿ ಈಗ ಆನ್ ಆಯ್ತಲ್ವಾ? ಈಗ ಮೀಟರ್ ಆನ್ ಮಾಡಿದ್ರ, ಈಗ ಫಸ್ಟು ನೀವೇನು ಮಾಡ್ತೀರಾ? ನೋ ಲೋಡ್ ರೀಡಿಂಗ್ ತಗೋತೀರಾ ಅಲ್ವಾ? ವೋಲ್ಟೇಜ್ ಏನು ಇಷ್ಟು ಗೊತ್ತೈತೆ? ಗೊತ್ತಾಯ್ತು ಈಗ ನೋಡಿ, ಅದನ್ನೂ ಇದು ಮಾಡ್ಬೇಕು ನಾವು.
ಕುಡಿಯತ್ಕಣ
ಕುಡಿತೈತೆ ಕಣ,
ಹೊಡಿತಾ ಹೇಳು.
188 ವೋಲ್ಟೇಜ್ ಆಗಿದೆ, ಆದರೂ ಒಂದೊಂದ್ಸಲ ರಿವರ್ಸ್ ಹೊಡಿತದೆ. 189 ವೋಲ್ಟೇಜ್ ಬರ್ಕೊಂಡಪ್ಪ. 1.90 IL, S1 S2 S00, ಆಯ್ತಾ? ಸ್ಪೀಡ್ 1493 ಬರ್ಕೊಪ್ಪ. ಈಗ ನೀವು ಮೀಟ್ರ್ ಡೀಟೇಲ್ಸ್ ಬರ್ಕೋಬೇಕು. ಮೀಟ್ರ್ ಡೀಟೇಲ್ಸ್ ಅಲ್ಲ ಐತೆ. ಹಾಂ, ಇದು ಮೋಟ್ರದ್ದು ಡೀಟೇಲ್ಸ್ ಬರ್ಕೊಳ್ಳೋ. ಒಬ್ರು ಬರ್ಕೊಳ್ರೆ ಸಾಕು. ಬರೋ, ನೀನು ರೀಡಿಂಗ್ ತಗೊಬರೋ ನೀನು, ಆಮೇಲೆ ಬರ್ಕೊಳ್ಳಿ ಹೋಗ್ಬಿಡು. ಇದು ಮೋಟ್ರು 13 ಆಂಪ್ಸ್ ರೇಟೆಡ್ ಕರೆಂಟ್ ಇದೆ. ಅಪ್ ಟು 13 ಆಂಪ್ಸ್ ಗಂಟ ನಾವು ಲೋಡ್ ಅಪ್ಲೈ ಮಾಡ್ಕೊಂಡು ರೀಡಿಂಗ್ ತೊಗೊಂಡು ಹೋಗೋದು. ನೋಡಿ ಇಲ್ಲಿ ನೋಡ್ಕೊಳ್ಳಿ, ಇಲ್ಲಿ ಇದು 13 ಆಂಪ್ಸ್ ಬರೋ ತನಕೂ ರೀಡಿಂಗ್ ತೊಗೊಂಡು ಹೋಗೋದು. ನೋಡು, ಹಾಂ ತಗೊಳ್ರಪ್ಪ, ಈಗ ಇದೊಂದು ರೀಡಿಂಗ್ ತಗೊಳ್ರ.
ಸರ್ ಯಾವ್ದು ಬೇಕಾದ್ರೂ ರ್ಯಾಂಡಮ್ ಆಗಿ ತಗೋಬೋದು.
ಹೌದು, 13 ಒಳಗಡೆ ತಗೊಳ್ಳಿ. 4.59 ಫಸ್ಟು 187 ವೋಲ್ಟೇಜ್ ಬರ್ಕೊಂಡ್ರಾ, 4.42 ಕರೆಂಟ್ ತಗೊಂಡ್ರಾ, 1
4 ಕರೆಂಟ್
1433 ಸ್ಪೀಡ್ ಸ್ಲಿಪ್ ಹೇಳಿ, S1 S2 ಹೇಳಪ್ಪ, ಎಷ್ಟು ಅಂತ.
உங்களோட உங்களோடதாங்க ஒண்ணு லேப் எடுத்துட்டேன். அடுத்தது 3403 அது தெரியாது எனக்கு. இதுல எல்லாம் நெரிச்சாய் கிடைக்கா கீழே தெரிய மாட்டேன். சரி அஞ்சாவது மேடம் ஏரியா கொடுக்க இந்த டிஜிட்டல் டானிக்ஸ் பாடம் இருக்கிறதா இது டிஜிட்டல் இருக்கும். எப்படியாவது உட்காந்துருக்கும். மொபைல்ல தலைவலியாச்சு. நேற்றையும் பார்த்துட்டு தான் போனேன். அடுப்பாயிட்டு தூக்கி வச்சுட்டு போயிட்டு இல்லையேங்க. அதிகமா இதுவாதான் இருக்கும் போல. பிடிசி 8ஆம் தேதி நடந்துறாங்க. பேர் யாரு? பெர்லின். PDC 34031. EDC தேரி எத்தனை பேர் சொல்றோம் பாருங்க. சொல்றேன். அப்பதானே பாருங்க 40 41 10 10 ஒரே நிமிஷம் மேடம் இன்னைக்கு பார்த்தோம்னா கேட்டிருந்தீங்கன்னா டீட்டெயில் மேடம் பேசணும் இல்ல கூட்டிட்டு கேட்டதா நீங்க சொன்னீங்கன்னு சொல்லியே சொல்லுங்கன்னு கேட்டீங்கன்னா நாங்க எடுத்துட்டு வந்துருவோம் சார். இது எப்படி சார் இப்போ நம்ம பேசணும்னு வச்சுக்கோ சேர்மன் மாட்டிக்கா சார் பாருங்க சார் சொல்லி கேட்க அவர் டோட்டல் பார்த்துட்டு என்ன பேசுறாங்கன்னு பேசிக்கலாம். CA 3 தான் இல்லைங்க பார்த்துதாங்க இருக்கேன். ம் ஃபோன் பண்ண சொன்னாங்க. எனக்கு வினோத் சார் கால் பண்ணுங்க, கால் போக மாட்டேங்குது. வினோத் சார் கால் பண்ணி சொல்ல சொல்லுங்க. மறந்துடாப்ல. ஐயா அடை சார் ஃபோன் பண்ணி சொல்லிடுங்க இல்லையா, வந்துருச்சுங்க. கூப்பிட்டு அப்படியா? சரி ஓகே, பார்த்துங்க பேச போனீங்கன்னா சொல்லுங்க. ஓகே சொல்லிடுறேன். இல்லை ஃபோன் எடுக்கலையா? அப்படியா மேடம்? ஆமா மேடம். அப்பப்போ சூட அனுப்பிடுறாரு. இங்கதான் பக்கத்துல தான் இருக்கான். நீங்க நாகூரா என்னமோ தான் மேடம். நீ அனுப்புனியா கொஸ்டின் பேப்பர்லாம் அனுப்புனீங்களா?